Welcome, everyone. Let me share my window here.
So pretty, by the way.
Yeah, I was playing around with this new presentation tool, Gamma.ai, and I can't go back to PowerPoint ever again. So
That is huge praise. Yeah, a friend of mine actually quit to work for this company, and I was like, another AI slides company, these never work. Uh, Shows what I know.
it's really impressive. So I not paid by the company in any way, but do recommend people try. Uh, so This week, we're going to talk about a new paper out of Google Research, uh, Titans. The main thing that this new architecture presents is giving the model some memory, especially at inference time, so that it can leverage that to make better inferences and improve benchmark scores. And I'm generally not going to be looking at the chat while I present. There's a lot to go through, but I'm going to leave plenty of time at the end for discussion where we can go back over questions. So yeah, so do feel free to drop chats in or drop posts in the chat, and we will get to them. So let's see. Okay, I'm trying to figure out how to. Oh, wait a minute. There we go. Okay. Um, so what are some of the problems that this Titans paper is trying to address? The the first of which is the quadratic complexity nature of attention. And this has been one of the things that um, typically was up until say the last year or so really restricting the context window size of models. So I, if I remember correctly, when GPT-4 came out, it first had like a size of 8K or 32K, something like that context window, but nothing compared to the like 1 million context window of Gemini. And the reason was that for in typical attention, every token is compared to every other token so that if you say have a context window size of 1,000, then the complexity is 1,000 squared. And if you have a you know uh, window size of 10,000, then it's 10,000 squared. And so in order to increase the size of your context window, it becomes like very computationally expensive very quickly. And there are ways around this that are mentioned in the paper, but that's one of the problems with, let's say, classical transformers, which leads right into the limited context window, uh, again, based on the quadratic aspect. And then the other thing is that uh, the long context window create creates the bottleneck for the very long processes, very long sequences of data. So transformers are great, and there's been tons of advances in them since the attention is all you need paper, but uh, there are limitations in their architecture. And so, what does Titans do to try to address that at a very high level? The first thing it does is to emulate human memory, uh, meaning that human memory has different, you can think of them as modules or types of memory. There's short-term memory and long-term memory. Um, However, in the typical transformer model, as we'll see, those have like short-term memory because they have access to the tokens that they're currently processing, but anything that happened before that, they don't have memory of that. And as you do AI engineering, you probably are well aware that every time you make an API call to OpenAI or Claude, it's like starting all over again. And then the second part is the enhanced processing. So the memory allows very long, like extremely long sequences to be handled so that, and we'll see that as the tokens are processed, the model keeps a representation of just the most salient or important, uh, let's say facts. It's a representation of facts, but let's say facts from the tokens it's seen so far so that it can use those to improve predictions on future tokens. So there was some work by other groups and this group as well. So this isn't like a sudden thing. This paper, test time training with supervision, goes back to 2020. So there's a few things that this paper represented. The first is using that unlabeled test data set into a self-supervised learning problem so that it can update its own parameters before making a prediction. And they noticed performance improvements with this. So that's one paper that previously came out. And I'm going to just mention two papers. I didn't read either of them in depth. I just kind of read the abstract and got the gist of them. But if you're very interested in this, both of these are good sources. And then the other one is this RNNs or learning to learn at test time about RNNs with expressive hidden states. So this is, and we'll see this in the Titans paper as well, that it does bring an RNN or recurring neural network technique back into transformers where there is a state inside it's the hidden state. And as the tokens are processed, that hidden state is updated and then allowed to affect future outputs. So this is the paper that brought that into the research community. You can also see one of the main points from this paper is the linear complexity. So using this to get around the quadratic complexity of the typical transformer. So as I mentioned, Titans is inspired by human memory. There's core or short-term memory. So in the Titans models, this is the equivalent of just the normal attention mechanism where you have the query keys and values sets, all interacting in the transformer component. So this is the short-term memory. So they don't really introduce anything about short-term memory. They just reuse what is already out there. Long-term memory is where they learn to memorize historical context, encode that context into abstractions so that it can improve future tokens. This is the main thing that they talk about in the paper is this long-term memory module and how exactly it operates. And then the persistent memory is not a like inference dependent thing. So this is you can think of this as like a set of knowledge or a set of rules that always exists in the model. It's hard coded in there, and it's always brought into the uh, into the sequence. We'll see how that happens. They don't talk a whole lot about persistent memory, so it's, at least for me, it was a little unclear how exactly this is created, but it's also not the main point of it. It's just kind of a set of parameters that are always fed into the um, sequence that's going to be predicted against. Okay, so let's take some time digging into this long-term memory module. So this is the kind of the main breakthrough that this paper is presenting. There's a few different things you can see here as far as what this module does. The first is recurrent processing. So like I mentioned, it maintains a state as it's doing inference, and then that um, part of the output is then fed back into that state so that it can continue to capture new information and as it goes along. This helps it to kind of learn the task that it's doing, and also to do those needle in a haystack things where maybe some information early on in the sequence is relevant to something much later, so it can keep that in memory. It's also a memory component, so this is the thing that is responsible for generating representations for um, the information that is coming through it at inference time. And then let's see, the last bullet point about sequential data handling. Yeah, so as I've been mentioning, like we're assuming this is all happening in a sequence of tokens, and in the case of a large language model, where it's processing one token after another, it's not all at once. Um, that's uh, pretty taken for granted for any large language model. So let's keep going. So we'll dig into a few different aspects now of the uh, long-term memory module. So here you can see some points. Let me pull out a couple of them. One is this weight adjustments, which is, I think, one of the most interesting things about the Titans architecture. So for like almost all LLMs, or at least the ones that I'm aware of, like a GPT-4, a Sonnet, Claude Sonnet, whatever, they do a lot of pre-training. They do, instruction tuning, all of that. But once they're done with that, then the weights are just the weights. And even if you think of like the DeepSeek release last week, like it's just a bunch of weights. So these don't adjust in memory, no matter what you put through the model. Whereas this Titans model, at least in the context of a single inference, can adjust weights on the long-term memory module, which I think makes it like a very interesting new approach. And it for the continuous adaptation, so that's kind of plays off the weight adjustments. So that's something that, as it's going through a long sequence of perhaps even millions of tokens, it can continue to actually learn um, about like the data that it's processing. And that's another thing that they really emphasize in the paper is creating a model of, when I say model, I don't mean like a machine learning model, I mean like an abstraction for learning, and what does that mean for a model to be able to learn. So, um, so we've talked about how the model updates its weights based on the data that comes through. And so how does the model know like what is interesting, like what is worth keeping and what isn't? Because it doesn't have enough parameters for long sequences to capture everything that comes into it. So it's going to have to compress whatever data is coming through. So how does it decide how, like what to remember and what not to? So this surprise mechanism is the main way that it does. So information that's considered surprising is is for humans more memorable, and so they took the leap that for a model, it's also going to be more memorable or more important to remember. Just looking through the slide. So, okay, so the point is, well, how do we know if information is important or not? The main way they decide that is the gradient of the neural network with respect to the input data. So you can see that, hopefully you can see my mouse, but you can see that down here, the gradient of this incoming input data with respect to the memory from the previous time step gives us the amount of surprise. And you can see it gives preferential treatment to this surprising information. The more surprising it is, the more likely it is to be stored in memory. So you can imagine for like a long sequence of maybe documents, maybe there's, I don't know, 100 documents that are all legal briefings, and then it comes to something that is maybe a bill of lading or uh, a product description or something like that. So then it's gonna be like, oh, this is completely different. I should remember something about this. So it's gonna prioritize keeping uh, what it considers surprising or information that it hasn't seen before. And then it stores this in key value pairs in that uh, long-term memory module. So in addition to surprise, there's also forgetting. So, oh, I should have mentioned in the um, last slide that this theta parameter here controls the amount of like kind of the impact of surprise. So it's a tunable parameter that can be increased or decreased to either remember more surprising information or forget it. The momentum and dynamic forgetting means that it can forget things so that it does discard irrelevant information as it goes along. So there's this, you can see this 1 over alpha, where it is slowly degrading the older memory. So as things get older and older, they fade out. Is there, I heard someone come off mute. Is there a question?
Yeah, that MT parameter, is that the output of the memory module or the model itself?
That is essentially the state of the memory module.
Okay.
Yeah.
And so the surprise has the same dimensions, the same form as the memory itself.
Why don't we look in the paper after the presentation and we can, or if you want to look at it, I
Yeah, I
I
assume so.
can't
Just
answer
because
that
there's a
right off
simple,
the hand. What?
I would assume so, because it's just a simple addition
Yeah,
to it. And so kind of curious, I guess the origin of this is that, they show different structures for how the memory was included, and it's like added in different parts of the architecture stack, if you will. And kind of curious if that would stay the same across their form of the architecture, or if it changes depending on where the memory is included at.
yeah, that's an interesting question. I'm gonna go through the different architectures they introduced. So hopefully, I don't know if that'll answer the question, but at least it'll give us enough context for discussion. I'm going to leave plenty of time for discussion, so this would be a good thing to talk about then.
Cool. Thanks.
Yeah. And then it also has this momentum that where it combines past surprise with a decay factor. So that's this eta t and I guess the previous surprise. So somehow this provides a momentum mechanism to the model. Okay, so those are kind of the components that go into a Titans model. Now let's look at the different ways they combine them, because there was this open question of like, okay, we have this module that we think would be useful for the model. Like, let's see what's the best way to then incorporate that. And they come up with 3 different options: memory as context, memory as layer, and memory as gated branch. And each one of these has their strengths and weaknesses. So let's first look at the memory as context. And I'll just walk through this diagram a little bit. So we can start looking over here at this is the input sequence. So this is essentially your prompt, or what you are sending into the model. This is then used as a key or a query, I guess a query into the memory module that then returns like the most relevant information from the memory as a sequence of tokens. And then at the same time step, you can see this is the persistent memory. So this is kind of the hard-coded information that just always has the same tokens that adds to the sequence. So you can see that before we go to attention, we're adding these extra sequences. So in my previous example of like legal documents and maybe a product description, the retrieval could say like, okay, this sequence looks like, or this next part of the sequence looks like a legal document. So let's grab any information we have about the legal documents, put it here. And then this persistent memory might just be about how to generally handle incoming requests, something like that. Goes through attention. So this is the quadratic thing where every token pays attention to every other token. It then, based on the output, sends an update to the memory. So updates the actual weights here with whatever relevant information came out. Then I'm not sure what this is, some kind of maybe an XOR, combines these and then gives you the final output. And so this is what the attention masks look like for memory as context. You can see that each one of these is treated as like a small context window. So it's like kind of little batches of tokens being paid attention to together. Then we add the long-term memory onto that. And then finally, the persistent memory. And so this kind of gives you an idea of like inside the attention mechanism, what exactly it's seeing. Okay, next, memory as gate. So this is a different approach. It does not have it does not like query the memory before sending it into the attention mechanism. So it sends the query to the memory at the same time as going through the attention mechanism, and then combines them afterwards. And so the memory, like whatever is stored in the memory, does not go through the attention mechanism at all. Yeah, so this uses the memory as a gating mechanism, I guess right here, which I guess would allow, I'm assuming, allow certain tokens through and some tokens not. We can discuss this in the discussion about exactly how this works. And then here's the attention masks for the memory as gate. You can see it's quite different here. This is a sliding window that, you know, each token pays attention to a certain number of tokens on each side of it. You can see the long-term memory, how next to the input sequence, the memory is strong, and then it gradually fades out as the tokens are, further in the future, if you will. And then finally, the persistent memory just like adds to the very front of the sequence. So this is what the attention masks look like in the memory as gate. And then finally, memory as layer. So this is in some ways similar to what some transformer models do, where they have the attention mechanism and then there's a feed forward mechanism as well. So this is like the closest thing to that, where it just goes right into the memory. Whatever comes out of the memory goes into the attention. Yeah, and it says cannot take advantage of the complementary data processing of intention in the neural memory module. So there's no combining after, either before or after. It's just like one more step in the architecture. And then finally, they also in their experimentation look at memory without attention. So this is essentially just a long-term memory module by itself. There's no attention mechanism, and they just look at like, how does this perform? Just purely a long-term memory module without attention or anything. Okay, so now we're getting into the last part of the paper, the experimental setup and results. So they test all four of these variants, and they test them at different sizes. And I thought one thing that was interesting is that these are pretty small sizes, at least compared to, your modern LLM. So like a Llama 7B is considered a smaller model. And if you look at like a you know, like a GPT-4o that has probably hundreds of billions of parameters. So this size is pretty tiny compared to like the models we use day to day. So they gave a big table of the results for language modeling, and they also threw some common sense reasoning benchmarks into here. So you can see all the benchmark names across the top, and then the best performing ones are highlighted. The tan highlights are for hybrids, and then the blue highlights are for, I forget if it's pure or just like normal, or yeah. So you can see that basically Titans wins at everything here versus Mamba, DeltaNet. Um, this is test at the time of, or no. Anyway, this is one of the previous works of memory testing. So you can see that it wins at everything. This is for the 340 million parameter model. And you can also see the number of tokens they train on is pretty small. Modern LLMs train on like low trillions of tokens. So this is not much data at all. Then, so you can see like language modeling, it does quite well. And then here's their needle in a haystack. So for this test, they had some information early on in a sequence and then a bunch of like filler tokens and then some sequence that needed those very early tokens, like to understand what was happening. And so you can, Titans is the red stars here. So you can see that they are maintaining their performance quite well, even out to here, if we go to the fine tuning setup, 10 to the 7th, so even out to 10 million tokens. I mean, they did take a performance hit, but still doing much better than every other model. And so I think this is, for me, one of the most interesting charts that just shows that as this becomes more productionalized, there's going to be the opportunity to have longer and longer context windows where maybe you can feed in like a bunch of YouTube videos, like hundreds of pages of PDFs and all this stuff, and still have it be give you like relevant output. So with that, that is the end of my presentation. So let me pop open the chat here. See what's going on. And if anyone wants to speak up, make comments, make any corrections to what I said, like I'm not an expert in this, and I'm also not an AI researcher. So if you have insights, would love to hear those. And also, if anyone has answers to questions, feel free to chime in. Again, like I'm not the expert on this paper. Like I read it and understand it, but I know there's a bunch of very smart people on this call. So with that, I'll open up the floor.
I can
question.
also help with questions, but I'm struggling with the chat window. So
Okay.
Yeah, I mean, I want to validate Cosmin's frustration with this paper. Yeah, I mean, look, like I think they did try to illustrate the memory mechanisms somewhat, but not super, it's not super clear. And I always wish that these things came with code. I really like the name of papers with code because this one needed code. Um, And maybe they released it, but I didn't see it inside of the paper.
They
Yeah,
said
so
at the very
my
bottom of the
que-
paper that they're planning to release code soon,
How Chinese of them?
whatever that means.
yeah, I didn't understand if the diagrams refer to one step or multiple steps. Like I think in the and also the diagrams are 3D, which makes it a bit more confusing. Like they say, when you update a memory, you do memory of query, and then you get a like vector as output. What does that mean? Is that k nearest neighbor lookup? Is it some attention? Maybe we can go to the first slide where they update the memory equation. I don't know, Eugene, if you got any time to look, but I would be interested in just one of those operations. How does it actually happen? Like I understand at the high level we have a memory module, we update, it's nice to forget, they somehow figured it out, but like what layers or what do they actually do? Like even lower, you have some, if you go a bit lower. Yeah, you see
Retrieving
there's
memory here.
M star. Yeah, what does that? Maybe I didn't read, or like even this figure one, I didn't understand at all what's going on.
Yeah, I also skipped this because I didn't understand what was going on.
I can explain the in-context learning one with and I can with the parallels of what happens on RWKV7 and Titan based on what I understood from the paper. So think of it as this way. If
Which
let's
image?
say
Which figure?
this whole segment, the long-term memory training and the surprise formula, it's actually a lot easier if you explain it using simplified
Do you mind
code.
saying which? So we read while you explain. No, this is great, like having an expert explain it, but which figure is it or which formula?
So you scroll up. I'm trying to like figure out the page numbers as well. So we are talking about very specifically the segment 3.1 and the surprise metric there downwards, that whole memory architecture. So one way to view it, right, is that let's just say a standard prompt, let's say the quick brown fox, correct? And this is a piece of text that exists in so many training corpus that all LLMs will probably memorize this phrase itself, the quick brown fox. There is no surprise there. So because the surprise score is 0, there's no back propagation required per se to update the memories. If you view the memories as let's just say a 4,000, I don't know what's the dimensions here because they never disclose, but let's just say a 4,000 by 4,000, 4096 floating point value. In RWK case is BF16. If let's say we said the quick brown deer, then the model is like, hey, I wasn't expecting deer, I'm expecting fox. There's a difference there. That difference there, I'm oversimplifying the math because this is not accurate, can be converted to a loss score that you can back propagate on. So it's when you see that, when the model see differences, do you update this memory, this memory that's being shared between tokens? Now, where it differs for the Google paper, Titan and RWKV, which we are testing as well, is that the idea that
Eugene, so you have a separate key value store that you
yes,
you attend at the same time as you attend the current token. So
correct,
some frozen, that's your budget, right? And you
correct.
can attend the whole thing, okay? And
So
does that help or doesn't it help? And when it's surprising, you need to update. So I wonder how they send the update to the key value store. Like what actually happens? Like what's the loss of the key value store and the current token? Go ahead.
view if you want to view it as simplified code, which is not how they implement it, because is that you can view your model weights during the forward pass, right, as frozen, just view as frozen. And the quick brown, let's say the quick brown, those tokens, right, generate a state. You take that state, and then let's say instead of, let's say we see fox and then we say deer instead, right, there is a difference in expectation. The model expected fox, it got deer instead. So because the model weights are frozen, if you do the forward pass and then you want to correct the model's thinking and you do the backwards pass, the only way to update it is this state value. So you do the backwards pass, you update the state values, then you take that state and you process the next token. So you continue your sentence completion. And that essentially is what the surprise mechanic is about. It's about, hey, it didn't give the output we required, and then we take that difference and then we convert it into a score. Where this differs from RWKV is that we don't use a surprise mechanism. We are currently using more closer to the standard gradient descent. So the difference here is that in a surprise mechanism, so if let's say you expected fox, and you get fox, for example, there's no back, the loss is essentially 0. There's no back prop. But in RWKV's case, right, if let's say it expected fox and it actually got the fox, and since the way logics work, there's always a 0. Let's just say 0 point something % different. There's still a loss score being calculated there. So even though it was not a surprise, we still do the backpropagation process. In practice, is this better or worse? I have absolutely no idea. This is something we need to test and elaborate on. But that's the key difference on how we handle the memories segment. It's all about like every token you forward, you backprop and then you update the weight. This is probably
So you
the
just update
simplified
the
way.
key value store instead of
Correct.
you propagate the signal through the frozen weights and just update the keys and values. One
Correct.
more question that I got was how do they manage a fixed size key value store? Basically, how do they decide what to drop and stuff? And they have this, I didn't understand their gating in here, but basically, yeah, over time you'll see lots and lots and lots of things. So you kind of need to figure out, like, if you're efficiently using your memory, then you solve the problem basically.
So this is where it goes to the AI black box. We decide the key value store to a specific size. That's part of the architecture design. This is the same thing as the model dimensions. As to how the model decides what to keep and drop, right? That is specifically decided by the model. So I think there's another segment that where it highlights the decay, right? Let me find that segment.
Yeah,
Decay,
could you scroll
decay.
a bit down? Because
I believe yeah. Sorry if I'm not looking at the screen because I'm looking at the paper to just find the
Yeah.
decay. I
Sure.
think it was mentioned.
yeah, it's a forgetting mechanism. Sorry, it's
Oh.
yeah.
Right
It's
here.
equation 13.
Yeah, so the idea behind the decay mechanism, right? And this part is consistent with other theory is that by default, every token you move forward, you are slowly forgetting. And the forget rate, right, is something that's trained in the model. So let's just say the value is by default, everything you will forget in 32K tokens. So if you forward 32K, you should forget it. This makes it sound similar to sliding window attention in that sense, but the decay mechanism is supposed to work together with let's say the surprise mechanism or basically the models. This is a bit more gray, but basically as by default you decay, you let the model compute against the state itself, and the model may just decide, hey, this is important to memorize, so I'm going to reinforce that number. So as every step it takes, right, in a way, internally the model just like keeps back propagating against the state and think, hey, do I need to reinforce this floating point value? If I stop reinforcing it, it will eventually decay. But if I want to reinforce it, I can just like keep increasing the value and then keeping it within bounds. And that's how it keeps kind of like by default it will slowly forget. But if it thinks it's important, it will keep trying to remember it over larger context time. To be clear, this part is really theory crafting because even for RWKV, the highest we ever push a model to is 32K, and we are now experimenting 64K. This theory crafting is supposed to like extend to like 1 million token per se. So it's something that we definitely need to test. But the idea behind decay is so that by default things will expire, and so the model is able to clear up space to memorize new things, and it's able to also decide for itself to keep things in memory. Not much different from how they describe it in Titan. Yeah.
Thanks a lot. This helped me quite a bit.
Eugene, I have a question. So when you're referring to by default it decays, so in terms of the surprise here, can we assume that the surprise by default is low for most of the tokens?
I think view it as let's just view it as a RAG scenario. A RAG scenario. Let's just say your company is the most generic company on earth. And then I just put your company document there. There is no surprise. Then it just moves on. But let's just say your company has some very proprietary, never heard before stuff. That surprise will then be what is stored. So it's about the difference in information in the fixed model weights compared to this floating point state. Does that make sense?
Yeah, makes sense. Thanks.
Is there any other? I'm trying to read the questions from the chat.
Yeah. There's another one from Cosmin earlier about our needle in the haystacks, interesting tasks. I mean, I think they could be in real use cases. There's probably a lot where they're not, but depending on your use case, I could see how if you just want to throw a bunch of tokens into the model and not worry about like the order or anything, that it would be useful to have.
I think
Okay.
it's interesting also academically to just understand the maximum limit the model can memorize in worst case scenario. That's the way I view needle in the haystack. In practical scenarios, like I say, because surprise that was one of the challenges about this about RWKV benchmarking this as well and the same thing for Titan, is that if let's say we train on Harry Potter book and you just put the whole Harry Potter book as the right context, there's no surprise there. And essentially it can pass the RAG test with what 300k context length, but that's not a correct test per se. So neither in haystack is meant to represent the worst case scenario. That's what I feel. And a lot of companies are a lot more generic than they think they are. Also, like I think in NeurIPS, right? The joint presentation that we did with Dan Fu, right? Both him and I agree that that like with other techniques such as repeating twice, that works well for both Mamba and RWKV, right? Is that we may want to reevaluate how we benchmark these things per se, when it comes to like practical RAG situations. Because if let's say the inference cost for Mamba and RWKV is 100,000x cheaper, and its RAG performance triples or quadruples just by repeating the context twice. So then we just repeat the context twice. that was one of the arguments. And I kind of agree that, but it's also a very different test.
I see there's another question, Eugene, that you'd be good at answering is what is the gating mechanism in modern RNNs?
What do you mean by modern RNN?
I don't know. Aditya, do you want to clarify?
I have the sentences on the paper right in front of us. It says Dow and Gu 2024 or Vieto et al. 2023. So it's with comparison with the weight decay mechanism. So I just had no concept RNNs normally do. That's relatable.
Oh, okay. Later weight decay mechanism related to. I may need
what
to
page?
dig in deeper on that. Is it page 6? later in the section, we show that the weight decay is closely related to the gating mechanism in RNNs, DAO and Gu, citing, I presume, the Mamba stuff. Yeah, okay, state space model. Yeah, it's citing the state space model. This would be similar to the weight decay that I explained earlier. Which is basically by default is forgetting.
So my understanding of Mamba is that they run these RNNs without gates, so that they can run something like fast Fourier transform or some parallel scan on GPUs and run it fast. And then they have some multiplicative process on each token. And when you do multiplications, basically you can use them as gates to how much of the signal you propagate. So they add the nonlinearity and gating at token level. While old school LSTM, they had memory gate, forget gate, input gate at each step, and they would running it one by one. So it might be, that might be one thing, like this token level multiplicative things that people have in state space models.
Yeah, if it's about that, then it's really more about how we restructure. So both Mamba and RWKV and Titan is that with the way we restructure the formulation, we do not need to wait for one token compared to another, unlike the OLSTM. So yeah, I think that makes sense. Yeah, I think your explanation makes more sense. Basically, if you contrast it with the OLSTM RNNs, all the newer gates, even though we are designed differently, is designed in a way that doesn't have this bottleneck, where you need to wait for one token after another. Whether is it through math hacks, which is what a state space model did, which is really impressive, honestly. That kind of math. But that's what they are good at. And in our case, it's really more of like how we optimize things at the CUDA forward. It achieves the same result. It's able to train in parallel. Unlike ORNNs. And I'm quite sure Google has their own optimization when it comes to training as well.
I had another question, Eugene, for you. Like, I don't know how to compare baselines with this model. Like, are you impressed with 1 point perplexity win on Wiki or the other wins? Or it's kind of any new model usually shows that kind of win. So to me, the wins seem large. So I think, is this something super strong or it's okay, not great?
To be honest, I classify this in promising, but we need to test further because, like, even in our experience for RWKV, like anything below 1.5B, right, may not necessarily hold until 7B kind of situation. So we had revisited like experimental changes where we made on 0.5B models, which is kind of like what's being tested here. Here is 340 to 760 million parents, where the perplexity loss was great. It dropped much lower, and then when we scale it to 1.5B, it sucked. So it's promising, but I want to test to find out more because I think the true test is testing on higher on 1.5 and then 7B, which, to be honest, I'm quite sure the Google folks have done it. They are not compute bound. It takes more effort for them to write this paper than to train that 1.5B and 7B model. So
yeah, I'm a bit skeptical because there's some gossip that Googlers aren't allowed to publish super impactful stuff. So that it's interesting.
yeah, I also would like to know what was your results for the larger models.
Thank you.
Yeah, I mean, I guess that's one interesting thing is that, back in 2018, the attention is all you need days, Google researchers could publish anything they wanted because there was really no competitive advantage they were giving away. But now these days you wonder, like, if they have a really big breakthrough, are they going to publish that or are they just going to keep it to themselves?
I have another question. Sorry, if someone could explain the memory module is described as a meta in context model. In like quasi layman's terms, what would a meta in context model mean? There's like a sort of a parallel small model running on that's like as if it was trained very quickly.
So that's the part where I explained every time the tokens looks different from what you expected, it does the back propagation to the memory modules. So you can think of it as I'm oversimplifying the math calling it back propagation. Yeah, you can think of it as training the memory modules. If like it's inefficient to do it that way because we use matrix multiplication math dedicated for this. But in theory, you could implement it as your standard backprop gradient descent. At least for RWQ case, I may need double check for Google's case.
Thanks.
But the important thing is it runs at inference time. So it's
Right.
like it always backpropagates something, which is very different from other models that are trained in a big pre-training run and then nothing changes. You just run inference. So it's kind of meta learning that at inference time it still does some additional update.
Yeah, the long-term hope and goal, if we can get this process to be stable, and the memory module is, let's just say, 1 GB in size in memory, this is what will represent short to mid-term memories for AGI kind of like kind of model. The issue for any super long context training we're talking about in AGI scale is that we don't really have the means to really figure out how to train this memory module in a structured, guided way. And right now, the hope is that if we train it, let's just say at 48K or 32K, it generalizes to 1 to 8. And if let's say we train at 1 mil, it generalizes to 10 mil. So if we train it on 10 mil, it generalizes to a larger context length and much longer context length. The problem with this approach is, even for us right now, and this is something that maybe Titan may have more tests on, is that when we train on 512, it generalizes up to 4K and then it dies off there. Then if we train up to 4K, it generalizes up to 16 or 16K. So the generalization doesn't go on to infinitum, unlike humans, arguably. But then again, maybe that's why we go senile at the age of 100. Maybe that's the reason.
That's our context length.
Yes.
So I see we're at time. I don't know, Swix, I'll turn the floor back over to you. Any comments or thoughts about next week or announcements?
Ishan is doing GPT-2 on a spreadsheet. Is that Ishan? I don't know. He likes spreadsheets. That's all I know. So that will be next week. Okay, well, yeah, I mean, okay, I think that was a yes. Cool. Yeah, we have run out of our context length for this session, and thank you, Eric, for a great presentation. Yeah, very, very topical paper. I've just been chatting with Vibhu, and we're basically kind of thinking about doing the second paper club, and somewhat splitting between timeless papers or timeless survey papers, and then hot individual papers is kind of like the split that we're thinking about, and then also maybe doing it at a different time, so it's not like during the work day for most people in the US. So yeah, people are interested in timeless papers and then also hot papers. So I think those are the two spiky things, and maybe we can have a different vibe for that as well. Yeah, let's discuss in Discord, but otherwise, have a wonderful day.
See ya.
Bye.